Okay, everyone, let's get started. Remember, Lab 3 is due tonight. Dahlin sent an email out saying that he'll be available to help from 6 to 8 tonight if you still need to finish up the lab. If you can't get it done tonight, not a big deal. Remember, the late penalty is 10% or 10% per day, capped at 30%. Any major issues with Lab 2? Seems like things have been going pretty smoothly. Okay, so moving on to Lab 3. Those of you that got Lab 2 working probably noticed that it's pretty slow. How, anyone have any performance numbers?
It takes about 1.5 minutes for it to print out.
1.5 minutes?
Yeah, 1 minute and 28 seconds.
Wow.
Depending on my loop, but yeah.
Minute per frame. Yeah, that's pretty slow.
I actually said that because I think I just wanted to have fun.
Yeah.
And I looked at the for loops and the size of the array and the size of the screen. And did a bunch of calculations on it.
Well, that's what we want to do. That's what we want to do in this lab. Actually, we want to try to figure out why it's so slow, and make it faster. So the time per frame, it's going to be the number of pixels, which is 320 times 240 multiplied by the time it takes per pixel. The number of pixels is not something we can do anything about unless we lower the resolution, which we've already lowered it from the default of 640 by 40 down to 320 by 240. Right? The time per pixel is the number of cycles it takes per pixel multiplied by the clock period. The clock period is, at this point, for all practical purposes, it's fixed at 50 megahertz. So the cycles per pixel is the number of instructions per pixel times the number of cycles per instruction. So the instructions per pixel is determined by the instruction set architecture and also by the compiler and the programmer. You know, how efficiently you write your code and how efficiently the compiler generates the code, right? So the instructions per pixel is kind of a software thing, essentially. The number of cycles per instruction is influenced by things in the microarchitecture like stalls. Stalls can result from data hazards or control hazards. You guys, stuff you learned about in 212. And also cache misses. If you get a cache miss, you have to stall while you service the miss, while the cache services the miss. You guys remember that from 212? This processor, like just about any embedded processor, including the high-end ones that are in your iPhone 10, they use an in-order instruction architecture, which means that unlike a desktop or server processor, instructions aren't allowed to cut in line. So if you have an instruction that generates something that causes a stall, like a cache miss or a data dependency or a branch misprediction, it's going to hold up every instruction behind it. Now if this happens on a desktop CPU, instructions behind the stalled instruction can skip in front because the processors can execute instructions out of order, potentially. But that's not the case in any embedded processor as far as I know. Embedded processors are all in-order architectures, even, like I said, the big ARM Cortex-A processors. So what's my point here? Well, the performance has a software component and a hardware component. So in this class, we want to address both because we're doing software, hardware, co-design. So there's a few things we could do to speed speed up your code right away. Some of you might have already done this. The first thing is that this project uses floating point arithmetic when you do the image transformation. And I think I mentioned in class that the NIOS processor, even though it's implementing a MIPS instruction set, and MIPS has floating point instructions, which hopefully you learned a little bit about in 212, the NIOS does not have any of those at all. There are no NIOS 2 floating point instructions. So every time you do a floating point operation in your C code, the compiler is actually replacing those with subroutine calls to things like underscore underscore mul df3 and underscore underscore float sisf. Don't ask me what those do. I just I don't know. I don't know how to decompose those names into what they actually do. I just randomly grab those out of my own code. And when I say code, I mean the assembly language code that your C code is converted into. So the compiler is calling these subroutines, which then emulate floating point by performing the floating point operations using integer arithmetic. You guys hopefully did that in 212 as well. That's where you like if you do a floating point multiply, say, use integer instructions to take the floating point operands and tear them apart into their pieces, their sign bit, their exponent field, and their significant field, and then perform the multiply of the significance and then adjust the exponent and then repackage everything back together again. That's really slow, really slow. Like as compared to doing a floating point instruction, this is 100 times slower. Okay? So what do we do about that? How can we do floating point operations in hardware? Intel does this in a kind of a strange way. They have a module in the platform designer called custom floating point instructions. So if you go into Platform Builder and you go to the IP library and search for floating point, you'll see it. It's actually a module that you add to your system that connects to your NIOS processor through its custom instruction interface, which is kind of a cool concept because if you know Verilog, which any of you that took my 611 course know Verilog, you can design your own instructions and then package them into these IP blocks into Platform Designer and add them to the NIOS processor, meaning that you can add your own instructions to the NIOS instruction set. It's kind of cool. The problem, though, is when you look at the assembly code has a mnemonic, an instruction mnemonic called custom. So when you look at the software and you're having the software do these custom instructions, they're shown as an instruction called custom. So it's kind of hard to read the code. You don't really know what the custom instruction is from reading your software. You guys with me on this? Does that make sense? So what happens is that if you add the floating point instructions in Platform Designer, there's some neat stuff that happens where the BSP recognizes that you've done this, and it passes a switch to the compiler through the make file that tells the compiler to generate these custom instructions in place of where it would normally be calling these software emulated floating point operations as subroutine calls. You guys with me? So in other words, you add these custom instructions and the compiler will generate floating point instructions, but they're going to show up in your code as custom instead of as, mul.s or whatever the MIPS instruction is for single precision floating point multiply, for instance. You guys with me? So essentially what I'm saying is you go in Platform Designer, you add one component, and your speed should be about 100 times faster or so. Maybe not that fast, but it'll be significantly faster just by adding this module, and that's all you got to do. Well, you got to do this, and you got to rebuild your software, recompile your software. Make sense? Well, actually, to be a little bit more specific, you add this, you generate your design in Platform Builder, and then of course you have to regenerate your BSP, then you remake your software, right? And once you follow those steps and then just rerun it, reprogram the FPGA, then rerun your software, it'll be much faster, right? So we want to do that. The problem is that the floating point instructions are only single precision. They didn't implement double precision versions of these. Does it make sense? No, it doesn't. It doesn't make sense. I don't know why they didn't do that. Still waiting on, it's been 15 years, still waiting for them to add double precision support. So you have to also, in order for the compiler to use this custom floating point hardware, you have to make sure that your code only does float operations, not double operations. Now you might say, well, how do we know which one we're using? Well, there's one thing you can do is make sure that all of your variables are declared not as doubles but as floats. That's one. The other thing is, anytime you put in a scalar constant like 1.0, for instance, make sure you add a little f on the end of that, 1.0 and a lowercase f. Now that looks kind of weird, but what that is telling the compiler is that this is a constant, a floating point constant that is a single precision. By the default in C is if you put a number like 1, C thinks that's an integer. If you put 1.0 or 1.2 or 1 point anything, like if you put a decimal point, it'll assume that it's floating point, but double precision floating point. So if you put an F there, it'll tell the compiler that it should be a single precision. The other thing you could do is you could typecast it. You could put float in parentheses and then put 1.0. Or you could just put 1 for that matter, if there's no fractional part. Everyone with me? You all know the difference between double and single precision, right? Double precision is 64 bits and single precision is 32 bits. So there's a trade-off there. Double precision has more precision, it's more accurate, but it's much more expensive to implement in hardware. So, and so expensive, in fact, that Intel hasn't done it. So we want to use single precision. Also, functions like cosine, functions from the POSIX math library, like cosine, floor, round, those are also assumed to be double precision unless they have an F after the name. So floor F. So in other words, instead of using cosine, cos, you should use cos F. Instead of floor, you should use floor F. That's the single precision version. Question?
Yes, sir. So if we use double, because I'm pretty sure I've used doubles before, what exactly happens when we compile it and send it to the machine? Does it treat it as a float?
If you use doubles, it's going to call there's these underscore functions that are defined by GNU, part of the GNU, I guess they're part of libc or something. They're part of they're the same functions that you would have on any Linux / GNU type system. But there's a version for, you see this says mol df3. I think there's a mol dd3. So if you use double and you don't have hardware support, it's going to call the double precision version of the software routine to do that, and that's going to be slower. So it'll work. You'll get all the right answers and everything will behave, but it'll just be dog slow. You want to so you have to just be aware of that. So if you do single versus double in hardware, double is more expensive, it takes more transistors, and often the latency is longer. In software, it's just a question of the double is a lot slower if you're doing it in software. So these are the software routines, right? So right now, because none of you have, probably, some of you might have found this already, but most, if not all of you, have not added these custom hardware instructions for floating point yet. So all of your code, your compiled code, is using these software versions of the floating point operations, which are really slow. Okay, so that should make a big difference. And by the way, also, like when if you look at your assembly code, all of your assembly code, by the way, is inside of your, there's an object dump that's generated, lights.object dump. So it puts all the assembly in there so you can see it. It's kind of a long file because it's including the BSP code in there as well. But if you want to find where your code is at, you can just do a Control F and search the object dump for some snippet of your own code, some unique like signature of your own code. Like, I mean, you could search for main, but there's an alt main, and there's a couple different instances of the word main in there. But if you have like a variable that you declared that's kind of unique to your code, you can search for that and you'll go right to it. But anyway, the custom instructions, you'll see it's literally, it'll say custom, and then there's a couple, I think there's 3 registers or 4 registers, and one of those registers defines which custom instruction it's calling. So in order to figure out which custom instruction, like is that a divide, is that an add, is that a multiply, what is that doing? You need to go back and figure out one of the values of the arguments it sends in. So it's kind of hard to read in the code. Everyone with me? Make sense? Okay. Okay. This is a screenshot of what it looks like when you add that component. So I'm sure you can't read it in the back, but it says floating point hardware 2. Oh, right, there's 2 versions of this, by the way. I couldn't tell you what the difference is. I don't know off the top of my head. I assume the second version is the more performant version. So I used version 2. It probably doesn't matter too much, but I use version 2. So floating point hardware 2, and then it gives you a little table here. It shows you the number of cycles it takes to execute each of the operations that it supports. And it says actually up here, it says the version 2 offers improved performance and lower resource usage than the first generation, but it's at the expense of full IEEE 754 compliance with regard to subnormal support and uses simplified rounding modes. Nothing that is going to affect anything in this class. So version 2 works. Turn on everything, just leave everything on by default, and then just hit finish. And then once you add that, there's these 2 custom instruction slave connections. You have to hit the bubbles on both of those to connect them to your CPU. And there's only one CPU, so there's only one option there. So it's kind of a no-brainer, but you have to click that on and connect it. Everyone with me? Okay. Okay. Skip ahead here. There's one other thing you can do in addition to that to speed your existing code and hardware up. There is whenever you build your software currently, it's compiling it without optimization turned on. So GCC is not trying to generate your assembly code in a way that's fast. It's doing it in a way where each line of code in the C file has its own block of corresponding assembly instructions associated with it. And so that way, because it's under that constraint, it can't move things around or replicate code for the purpose of improving performance. The reason they do that is if you're using the debugger, you want to be able to have this correspondence between each line of code and one distinct block of assembly code. That way you can walk through your code with the debugger. If you turn on optimization, it speeds up your code, but it makes debugging kind of a nightmare because as you walk through your code, the debugger will act erratically because so basically when you optimize your code, it breaks the correspondence, the linkage. It breaks the direct linkage between your C code and your assembly code. It scrambles your assembly code up in a way that makes it so it's difficult to walk through it from the perspective of your high-level code. Does that make sense? You guys with me on that? I don't know if I explained that very well. But so generally speaking, when you're debugging, you don't use optimization. Once you're done debugging, you're convinced your code is working, then you turn on optimization and you get a free speed boost, because it's going to generate your code in a way that speeds things up. So the way you do that is you type you go into your software directory and you type software lights. You type NIOS 2 app update makefile app directory dot, it's current directory, set optimization -03. You guys with me? Now this is going to optimize your lights project. This will not optimize the BSP, but as far as I can tell, there's nothing that, the bottleneck of your code is not in the BSP. Someone may prove me wrong. I don't think optimizing the BSP will have a huge impact. You're certainly welcome to do that. In fact, you can. In fact, you just replace app with BSP here, and you can also optimize the BSP. But I think the real benefit here is from optimizing your app code, right? Any questions? So, yes?
How can you disable it after?
Just run that again with a 0 there. Good question. Yeah, there's 4 levels of optimization. 0, which is none, and then there's 1, 2, and 3. I've never noticed a huge difference between 1, 2, and 3. It depends on your software, obviously. I don't know exactly what GCC does to optimize. But there's a big difference between 0 and 1. So I usually use 3, which is the max. You might be able to use 4, actually, now I think about it. I think the later versions of GCC actually allow, there's a level 4. But yeah, but you can say 0 and it turns it off. 0. Okay. Okay, so just to reiterate, if you guys, when you finish your project and you submit it, feel free to do 2 very quick things to check to see how much it improves your performance. Add the hardware floating point, make sure there's no doubles in your C code, and then type that command in, and it should drastically improve performance just from those 2 things. Okay, so then what though? What do we do after that is the question. We need to figure out where the bottleneck is. Well, we have an idea of where the bottleneck is. I mean, this program is pretty simple. It essentially just goes through all the pixels and calculates colors. You know what it's doing because it only does one thing. But the question is the problem, if it's slow, is the problem because there's too many instructions? Or is it because there's too many stalls? There's too many cache misses or branch mispredictions or whatever causes these hardware stalls. In other words, is this a software problem or a hardware problem? What do we need to attack if we want to speed this thing up? If we want to tune this?
Hardware.
Well, we don't know. It's a good question. I mean, software-wise, let's think about this intuitively. What's going on inside your code? Well, basically, you're just doing an interpolation and an add. You can go inside your code and you can count up the number of arithmetic operations you're doing. It's probably something like 20, 30, right? So ideally, what do we think? Like, what would you imagine? How many instructions per pixel do you think this thing is doing? Well, at a minimum, it's got to do 1 instruction per arithmetic operation. So for every add, subtract, multiply, and divide that you have in your C code, there's got to have to be 1 instruction for each of those, right? But you've only got about 24 of those or so, maybe 20. I forget what, I counted them once, but there's roughly 20 operations. So we would expect it to be 20 instructions, right? About 20 instructions. Is that what it is? I don't know. You might be surprised. Because any more than 1 instruction per operation is just overhead, right? So how much overhead do we have here? So we need to figure out a way to count the number of instructions. We also need an idea of how many cycles it's taking per pixel, and this is kind of the same kind of math you can do. Like the MIPS processor is a RISC architecture. Generally speaking, it's 1 instruction per cycle. Ideally, it's pipelined RISC, right? So should be about 1 cycle per op, and if there's 20 to 30 ops per pixel, it should be 20 to 30 cycles per pixel, right? Is that what we're getting? I don't know. It seems like it'd be faster if that's what we're getting. So something's going on here. Something strange. So we need a way to count cycles, and we need a way to count instructions. You guys are using the interval timer now to time your code, but the interval timer has a granularity of 100 microseconds per tick. And the problem with the interval timer is it's going to slow, it's actually slowing, it itself is slowing down your code because it is based on an interrupt. Every 100 microseconds it generates an interrupt that interrupts whatever the CPU is doing and causes it to go and service, increment the tick counter. So it's got two problems. One, it's not precise, and two, it's got performance overhead associated with it. So we don't want to use the interval timer for performance analysis. We want to use a cycle counter. A cycle counter is a counter that just increments once per cycle, and it's like a peripheral that your software can read at any time it wants to read it. It doesn't have to rely on an interrupt and a global variable. You guys with me? Make sense? In fact, some people call these things performance counters. Every modern CPU has performance counters, or a performance monitoring unit. Performance counters allow you to count things like cycles, but generally speaking, they also allow you to count instructions and cache misses and branch mispredictions and load store instructions. But unfortunately, we don't have that ability. We only have the cycle counting ability with the NIOS, unfortunately. So we'll have to make do with that. So, so we want to add another peripheral called, they call it performance counter unit, but again, it's a misnomer because it's not really a performance counter. It's really just a cycle counter. They kind of oversold this thing a bit, in my opinion. But you add the performance counter unit in Platform Designer. And the only setting is the number of simultaneously measured sections, which is 3 by default. You can just accept that as 3 and then connect it as a slave on your data master port. So what is this thing? It's very simple. It's just a counter. And so the way you use it is you measure the current counter state, the current count. Then you run some code. Then you measure it again and subtract the original count, and whatever the difference is the number of cycles that have lapsed. So in other words, it works just like your interval timer, except it's cycles. So it measures time in increments of not 100 microseconds, but of 20 nanoseconds. And it doesn't have a performance overhead. You guys with me? Okay, good. Okay, so the way you use that thing is really simple. You have to add an include file for it, as you do whenever you add one of these, in general, whenever you add a peripheral. Except actually for the floating point instructions, you don't have to add an include file because the compiler exposes that functionality on your behalf. But this is a traditional peripheral. So you do it include Altera Avalon performance counter.h, and then you have to declare some place to put the cycle count. The performance counters, the cycle counters are 64 bits, which makes sense, right? Because if they were only 32 bits, they would roll over quite frequently, right? Because your cycle counter is going to go at 50 megahertz, and a 32-bit number will roll over at 4.2 billion. So if you take 4.2 billion and divide it by 50 million, you get something like 43 seconds or something like that. So it's like the odometer on your car rolling over every 43 seconds. So by having a 64-bit count, it guarantees that it will take a astronomically long time to roll over. Okay, but you have to be careful that in your code you declare those as an alt_u64, right? So in this case, I've got 3 variables declared: time 1, time 2, and cycles. Now you might say, did you declare those as local variables, or are they global variables, or where did you put those? It's up to you. Doesn't really matter. They can be global variables, local. I made mine local. I declared them in the function that I'm doing the measuring in, but it doesn't matter too much. Then there's a function called perf get total time, and then you have to pass in the base address of the performance counter, whatever that happens to be when you add it in Platform Designer. and that will just get you the current count. So now here's the crazy thing about that. For whatever reason, I don't know why, Intel decided that whenever you run this, whenever you call this function, perf get total time, it works, but then it turns the timer off. It turns the counter off. I don't know why they did that. So the crazy thing is that every time you grab the total count, you have to then follow up with a perf start measuring call, meaning turn the timer on. Not timer, counter. You guys with me?
Can you just pass it in? Can't you just pass in a pointer to that? If you have it inside a loop, you can just do that measuring thing. Pass it in a pointer, and every time it changes whenever it goes through the loop.
You mean just call it once instead of twice? Yeah, you could do that. Yeah, I mean, there's a couple ways you could do it. The way I did it is I called it, I said get total time, turn it back on because it turns off when you get total time. Then you have your whatever your pixel code is, and then I do the same thing again, except this time with time 2. So notice the first time I do is time 1, the second time I do is time 2, and then if you subtract those two, you're going to have the number of cycles it's spent inside the pixel code. Now you might say, wait a second, I mean, you're including whatever cycles are burned up in this function, in these two functions, right? Yeah, but hopefully it's small compared to the number of cycles that you're burning up inside that pixel code, right? So it's not perfect. It would be better if you didn't have to call a function, if you could just like directly pull that number out using a load instruction, and you can do that, but it's not worth the effort, to be honest with you. It's easier just to call their function. It's very low. It's just, in fact, you could look at their code. Go on the PSP, you can find that function inside the drivers directory. It's pretty small. In fact, I'll probably pull it up here in a minute. Any questions? So this will give you the number of cycles it takes for you to calculate a pixel. So if you're going to do this, you want to delete the interval timer. So delete the interval timer. Don't leave that in there. We don't need it anymore. Get rid of it. Also, make sure you go inside your BSP editor and turn it off in there as well, so the software doesn't still try to set up an interrupt for hardware that doesn't exist anymore. Okay? And then regenerate your BSP. Then turn on your compiler optimization, as I talked about earlier. Okay. Any question about that so far? So, floating point instructions, turn the optimization on in the compiler, delete the interval timer, add the performance counter. Okay, the next thing is, how do we count instructions? Now, you guys might be thinking, you're counting cycles and now you want to count instructions. Is that going overboard a little bit? Like, is that redundant? Is that gratuitous? No, because the instructions, like you might have a lot of cycles. Like you might find, oh, it's taken 70,000 clock cycles to calculate each pixel. That's ridiculous. That's outrageous. Why would it take 70,000 cycles to do 24 operations? Or something like that, right? But without knowing how many instructions was executed, we don't really have any way to interpret that information. You guys with me? Like, we need both pieces of information. We need to know how many cycles it takes, but we have to know how many instructions, because if there's a lot of instructions, that's because the compiler might not be doing a good job generating code, or you guys didn't do a good job writing the code for whatever reason. If the number of instructions is reasonable, but the number of cycles is high, then we know that there's some kind of weird hardware problem going on, right? There's something needs to be done with the hardware. The hardware is too slow, right? So we need to have the software performance and the hardware performance. And so having both allows us to calculate the number of instructions and the CPI, the cycles per instruction. You guys remember, hopefully you covered that in 212. CPI is the performance metric that unifies the hardware and the software together, because cycles per instruction says for every instruction, this is how many cycles. So for every primitive program construct, this is how it's implemented in the hardware, right? Performance-wise. So we need both. Okay, so how do we measure the number of instructions? Well, this is problematic because I have tried many different ways to make this work. This is tough. Ideally, we'd have a performance counter that just kept track of that, which you can do on Intel's processor or on ARM's processors, right? But we can't do that. We don't have hardware support for counting instructions. If you can't count instructions, the next thing is to generate an instruction trace. And the NIOS processor supports that, but they don't document how to get access to it because they license that functionality out to a third-party company in Germany. You have to buy some piece of hardware and license their software to get to use it. So I think it's possible to access that trace data, but I can't find any documentation. I have never been able to figure out how to do it. So how else can we count instructions? Well, last time I taught this class, I had everybody open the object dump and find their pixel code in there and just count them. But the problem with that approach was that if you count instructions inside the object dump, you're counting that's the static instruction count. That's the number of instructions that are generated. That's not the same as the dynamic instruction count, which is the actual instructions that are executed. You guys with me? Like, for example, if you have a code with a loop, you might only have 10 instructions in that loop, but when you run it, it may execute 1 billion instructions depending on how many times it goes through the loop. Likewise, in your code, I talked about how sometimes the compiler sneaks in these little calls. It calls functions that you didn't call. It just puts calls into functions. They usually start with underscore, underscore. And how do you incorporate the number of instructions executed by those functions in that case? You can't. It's too hard. It's a bad approach. If you talk to anyone that took this class last year, they'll probably tell you that was the kind of the most painful part of this class, was trying to figure out these counts. But this year, I think I have a better way to do it. I know I do. So we're going to use the debugger. So one of the advantages of using the command line tools as opposed to Eclipse is we have the command line GDB, and hopefully all of you guys have that working. If not, you're going to have to get it working for this lab. GDB is really powerful, and one of the things we can do with it is we can get the dynamic instruction count. It wasn't designed to do that, but we can do it. The question is, how do we get it set up to where it's easy to tell GDB to do that? The easiest way to do it, I have found, is to take your pixel code. And by the way, when I say pixel code, what I mean is everything that's in the loop body of your 4i, 4j loop, right? All the code that does the interpolation, the color blending, and the writing of the pixel. You guys with me? Just that's the hot loop, that's the bottleneck, that's the core, the kernel, the kernel, the middle part, that's the part that your code spends all the time in, is calculating those pixels, basically the interpolation. The transformation and the interpolation, that's your pixel loop. So you want to take that code and just put it into a function. That way, we can isolate that function from the rest of your code. Does that make sense? Okay? And I'll show you how to do that here in a minute. I'll demonstrate. One of the problems with doing that, though, is if you do that and you have compiler optimization on, which I just told you to turn on, one of the optimizations that GCC does is it will inline functions that are short. GCC is so smart that if you put your pixel loop, your pixel code into a function, GCC will take it out of the function for you again and basically copy and paste it. It'll replace the function call with a copy and pasted copy of the function body. That way, it can avoid the overheads of having to call a function over and over again. You guys with me on that? Right? That's called inlining. If the function is inlining, then it will break our ability to monitor it in GDB. So, there is an obscure C attribute that will tell the compiler not to do this. So it's underscore underscore. It's hard to tell from looking at this. There's two underscores there. Underscore underscore attribute, underscore underscore, and then two parentheses. I have no idea why there's two parentheses. Then there's a word no inline, and then two ending parentheses. And you want to put that between the return type and the function name. So if your function is like void my function, and then the parameter, the arguments, you're going to put that between the void and the name of the function. Make sense? It's strange, but you just do it. You just have to do it once to get things set up. Once you do that, you can open the object dump after you compile your code, and you can find that function in there. So in my example, the name of my function was called iteration. And after I built my software, I went into the lights.objectDump file, and I just searched for the name of that file, that routine, and it's right there in the symbol table, and that's the address. I highlighted it in red. Make sense? So you need that address. Once you've got that, then you run your code. So you open up GDB, you do target, remote, localhost, colon, or whatever port number you associated the GDB server. You load your program, and then you tell it to break star, which means contents of, in that address, which is the same address there, right? So I pull the address of my function out, and then I set a breakpoint on that address. I could have just said break. Actually, I could have just said break iteration, would have worked just as well, but you're going to need that address eventually. Okay, you guys with me? So if you do that, then when you run your code in the debugger, the first time it calls that function, it's going to stop. So you hit C, enter, it'll stop. Okay. Then do step I, step instruction. That'll go one instruction down. Then you type set pagination off. That just turns off, like in GDB. If you print something that's more than one screen size, it'll say print, hit enter to continue. Turns that off. Then you say set $count 0. So that sets a counter in GDB, a counter variable, and then you set up a while loop. You say while $program counter PC doesn't equal that address, the same address as above. Step I, set count equal 1 plus count or count plus 1, and then end. And that'll just run a loop in GDB where it'll just say step I, step I, step I, step I until the next time the function gets called. Right? So the assumption is that your function is being called for every pixel. So if you stop at the first time it's called, then you're going to do this, and the next time that function's called, it'll stop again. And it will record the number of instructions it had to step through in this count variable. So that'll give you a dynamic instruction count. You guys with me on that? It's pretty cool too, because it'll scroll. It'll actually show you what it's doing. GDB will show you not only the instructions, but it will also show you the corresponding line of source code as well. So you'll see your code, you'll see your C code scroll by, and under each line of C code, you'll see the instructions that correspond to that. So when you go back and look at it, you'll actually see which lines of code have more instructions than others, for instance. right? And this will be for 1 pixel. Because remember, you're calling this function for each pixel. Now you might say, well, why don't I just do this for the whole frame? It would be too slow. This is too slow to do for all the pixels. This is only practical to use for 1 pixel's worth of code, right? Anything longer, and you'd have to let it run overnight, because it's having to go through instruction by instruction. It's intervening after each. The debugger is intervening after every instruction over JTAG, so it's too slow for this to be done over a large segment of code, or a long sequence of code. Any questions? I'm excited about this. I think it's a cool idea. This will give you the number, like I said, and this will include any calls that the compiler put in. Okay. All right. All right, that's it. So we've covered that. Oh, let me give you, let's see, do I have time to demonstrate? Yes, I think I do. Yeah. Okay, so let me give you a little example here. So I have an example program, if I make it bigger. How do you, oh, there we go. Aha, okay. So here's an example program. This is not the same one that you guys have done, obviously, but this is just an example. I showed you this one, I think, last lecture or 2 lectures ago. This is a short program for calculating pi. This uses a simple and well-known iterative method for calculating pi, which is pi is 3 plus, and then it's 4 over 2 times 3 times 4 plus, minus 4 over 4 times 5 times 6 plus 4 over 6 times 7 times 8 plus 4, minus alternates plus and minus 4 over 8 times 9 times 10 plus 4 over 10 times 11 times 12 minus 4 over 12 times 13 times 14 plus 4 over 14 times 15 times 16, and so on. You see the pattern there? So you start out with 3, and then to calculate the fractional part of pi, it's an infinite sum where you alternate adding and subtracting. The numerators are always 4. The denominators are the product of 3 consecutive numbers that start with 2 and then increment by 2 each time through. Like that. So that's what this code does. So the more terms you add to this, the closer you get to pi. And actually, I've got this thing, I'm using double too, by the way, here. Val is the old value I calculated, and new val is the new value I calculated. And so the idea with this while loop is, as you keep adding terms, you're going to get so close that you won't have any more precision to get any closer. You'll be as close as you can get that double precision will allow. You guys with me? So that's why I say while val doesn't equal new val. And then it's just, starts, this 2, and then you just go through the loop. Okay, you guys might have seen this from, I don't know if you looked at this in my lecture slides. So how would we instrument this thing? Well, we have to take this code, this is kind of like your pixel code, and we got to take it out of that while loop, and we have to add a function for that. So I'm going to add a function void space underscore attribute parenthesis no inline parenthesis underscore space iteration, and then I'm going to just I'm going to paste my code in there like that. Make sense? There's a couple problems with this, though. The first problem is that obviously inside the while, I'm going to replace that with a call to iteration. Iteration. There you go. Done. but not so fast. I've got some variables I got to take care of here. The first problem is that the while loop is expecting iteration to calculate new val, and it also expects to have val. The old version is the old value is in val. So there's a couple little things we need to address here. First of all, this thing, I'm going to have it just return the new value, right? So I'm going to say new val equals iteration, and then this, whenever I calculate new val here, I'll just have it return new val, and then I'll declare that as a local variable up here, double new val, and then the old val, I will take that out and I'll move that down to here. And let's see, temp has to be moved up to that function. And then toggle is what controls whether you subtract or add. So I have a little toggle thing that it's whenever you want to add one of these, toggle is 0, and whenever you subtract, toggle is 1. So toggle, I will, actually, I'm going to declare that in here as a static int toggle equals 0, and take it out of here. And then do I need I? It doesn't do anything. I'll just take that out. Likewise, j. Don't need it. Anything else? Let's see, start. Oh yes, I also need start. Start is a double, and again, I'm going to make that a static. Does anyone know what that static does? I'm not sure if it's going to be relevant to your code, but just as a side note, static makes it essentially makes it a global variable, even though it's declared as a local variable, meaning that when I set a value of a static variable, and then I return from that function, normally when you return from a function, all the local variables, poof, are gone. But if it's static, when I come back in that function the next time around, it will retain its old value from the last time. And the way it does it is it just essentially makes it a global variable, but even though it's a global variable, it's still only readable from inside that function. So it's declared as a global variable, but inside the scope of that function. That's what static does. It's kind of cool. I think that's it. I'm going to get rid of ticks. All right, I think we're good, right? Is that it? Oh, temp, I've got temp, start. I think we're all good. All right, save it, and let's build it. All right, so hold on a second. Let me open a new terminal here. Got a source. I don't have this in my, is not automatic for me. Share, reconfig, get some files. Terra.bash. Data, designs, lights, VGA, software, lights. Okay, see if I can make this. I probably will get an error. Yes, line 7. I screw this up somehow. This attribute. Sorry. The double underscore goes under. I had the double underscore. The double underscore goes after the attribute right there. I had it after the no in line. Right? I get that right? And I just lost my mouse. Yes, there it is. Okay. So let me save that and rebuild. All right, there we go, done. Okay, so then if I look at lights.objectDump, so here's the object dump. There's a lot of stuff in here that looks kind of intimidating, but if you just search for iteration, you'll see it right there. So there's the address of iteration. See, that's the address. says a text means it's an instruction, it's instructions, and it's at that address. That's the symbol table that's being printed there. Okay. So see if I can get it to run. Let's go to positron where the FPGA is at. Source, share, reconfigs, files. And then let's go to data, designs, lights, VGA, software lights, and do NIOS, configure soft. Let me load, configure, oops, let's configure the output files. Lights.soft, there we go. Hopefully no one messed with my board. Oh, there we go, looks good. So I'm programming, this FPGA is physically attached to one of my lab machines upstairs. Good, and then NIOS GDB server, -- TCP port 8000, -- TCP persist, push it in the background, and I might have to rebuild that. Processor not responding. Okay. All right, well, let me try it. I doubt this will work, though. GDB lights.elf and target remote localhost 8000 load. Oh, looks good. Okay. All right. Now I can say break space iteration. Breakpoint is set. Notice the address. That address, it says, is the same one I pulled out of the object dump. And then I can do continue, and there it is. It got there. Notice that it's at that line with the no inline, attribute. So I can say next I. Then I can say set $count equals 0. Then I could say while $PC doesn't equal 0x08000006C. Right? Did I get that right? 1, 2, 3, 4 zeros. 1, 2, 3, 4. Okay. Then I can say set $count equals $count plus 1, next I, and then end. There it goes. Oh, I forgot to turn pagination off. That's why I just got that thing that says hit enter to continue. That would go away if okay, done. Now I can print $count. 64. So there are 64 instructions inside of this code, which is my kernel, my main. You can do the same thing with your pixel loop. Any questions?
Are you going to upload this code anywhere?
No, but I could. I mean, I could. It's not uploaded now, but I certainly could. It's actually on the slide. Well, not this version of it, not the outlined version. When you take code and put it in a function, it's outlining, and the opposite is inlining. Yeah, I can certainly do that. Okay. Any questions? All right. So one last thing then. What do we do? What do we do to improve things then? So we were able to improve performance a bit by compiler optimization and hardware floating point. How do we improve things even more? Well, here's another trick. We want to use, instead of floating point, we can use fixed point arithmetic. So the idea here is that You might say, wait a second, I thought we added floating point instructions, so that should be pretty fast now. Should be, but floating point, even the instructions have a long latency. In fact, I had the latency numbers were actually listed in the properties page right there. So if you do an add subtract, it's 5 cycles. If you do a divide, it's 16. If you do a multiply, it's 4, right? So every time you do a multiply or even add or subtract, it's taking anywhere from 4 to 5 times slower as compared to a normal integer instruction, which presumably has a latency of only 1 cycle. You guys with me? Right? So potentially we could get a speed up of 5 by not using floating point, even the instructions. And it turns out that you don't really need to use floating point. They're overkill for this application. We're only using it because it's convenient. But the fact is that we're only dealing with, We're only dealing with 8-bit colors here, right? Floating point gives us a lot more precision than 8 bits. We don't need that kind of precision. It's unnecessary. We don't need to have any more than 8 fractional bits, because if your weight, once your weight that you calculate in your interpolation code is less than 0.00000001 in binary, then that weight is essentially 0, because you're going to round down and you will contribute nothing. You guys with me? So we only need 8 bits of precision for color. Likewise, floating point gives us this huge dynamic range. The dynamic range is the ratio of the biggest number, which is 10 to the 38th power for single precision, down to 10 to the negative 38th power, right? So the dynamic range is the ratio of the largest magnitude number as compared to the smallest magnitude number, which is roughly 10 to the 76th power or something like that. And that's just for single precision. We don't need anywhere near that range because we're just dealing with 8-bit numbers and for color. And then with regards to the resolution of the screen, we only need actually 9 bits for that. Actually 10 bits, because a 10-bit sign number will give us a number between negative 512 and positive 511, if you remember from your 211, 212 stuff. So
You need unsigned ins anyway.
we don't need, we don't even need sign. You're right, that's a good point. But even if we allowed negative numbers, well, actually we do, because when you first do the transformation, it goes negative and you have to correct it. But even then, worst case scenario is 10 bits. We'd never need any more than 10 non-fractional bits, and we'll never need any more than 8 fractional bits. So floating point is way overkill for this. So let's use fixed point. You guys might have remembered fixed point from, I don't know if you guys covered this in 211, 212. I always cover it in 212 and 611, but you might have not had me for 212, or you might not have taken 611 yet. So fixed point is a very simple trick. It basically says, I want to use an integer for everything, but I still want to have fractional numbers. And so are integers restricted just to whole numbers? Well, no, because you can assume for a given value in an integer, you can just assume that the decimal point is somewhere in the middle of the number. You guys with me? So in other words, you just assume that there's a scalar. Like you say, I have a number, it's an integer, but whatever number is in there, it actually represents not ones, but 16ths. So that way, if my variable is 16, that really means it's 1. And if it's 1, it really means it's 1/16. Okay? So the idea is that you just fix the decimal point somewhere. So for example, this is a 6-bit number, but 4 of the bits I'm assuming are fractional bits, meaning that whatever's in this number, I'm just going to apply a scaling factor of 1/16. So that way, if I have 10.110, actually, well, if the number is 101101 in binary, which in hex would be 2 and that would be D, 2D in hex, right? Because that's a 2, 1101's a D in hex, right? So if I had that number, I would interpret it as being 2.1316, right? Why? Because if I look at the least significant 4 bits, I'm going to say those are fractional bits, so those represent 16ths. You guys with me? So that way, I can represent a fractional number without the cost of floating point. And you might say, well, why doesn't everyone use this instead of floating point then? Well, there's some drawbacks. Range, it has limited range, and it has limited precision. In fact, the precision is really problematic because the precision of a fixed point number is data dependent. The reason is you might say, wait a second, you got 6 bits, it has 6-bit precision. No, it depends on the number of leading zeros. This number has 6 bits of precision, yes, but that's because there just happens to be no leading zeros. So all 6 of those digits are significant digits. You guys with me? Now, but the thing is, though, is that when you're doing graphics code like we are, we know exactly what the range is ahead of time, and we know exactly what the precision needs to be. We need to have 8 fractional bits because we have 8-bit color, and we need to have at least 8 bits, or 10 bits rather, to the left of the decimal point. And in total, that's only 18 bits, and we have 32 bits in integer, so we're good. You guys with me? So all you got to do is use a fixed point format that assumes that you can have 8 fractional bits. Okay, now what's the problem? What makes this hard? The problem is that C does not have any built-in idioms for fixed point. This is something that's got to be implemented entirely by you as the programmer. Right? And you might say, can I declare a variable as fixed point? No, you declare it as an integer, and then at different points of the code, you make assumptions about where the decimal point is in that integer. Guys with me? Okay, so here's how it works. In this code, specifically, in this application, we do an image transformation. Let's start with that. That requires a sine and cosine calculation. Now remember that sine and cosine are going to give you a value that's between -1 and 1. Both of them, right? Now we don't have a way to do fixed point sine and cosine, so we will, every time you have a new rotation angle, so you're going to set your rotation angle outside your pixel loop, right? So you'll have a rotation angle theta, and you can say integer my cosine val equals, then you can say cosine f of theta. This will return a float, but you can apply your scaling factor right then and there. So if I want to have 9 bits, if I want to have 9 or 8? Let's say 8 fractional bits. If I want 8 fractional bits, then I multiply this by 256.0f, right? So that will scale this up. So that would mean that if the cosine value is a 1, the answer to this is going to be 256. Because when I convert it to an integer, that integer will have a 1 and 8 zeros after it. You guys with me? So then I can cast this as an int. Right? So this way, I calculate the cosine. I scale it by 2 to the 8th power, why 8? Because I want 8 fractional bits. And then I cast it back to an integer. So then my cosine value, in my mind, as a programmer, I know that this is a 32.8 value, meaning it's 32 total bits, and there's 8 fractional bits. The low order 8 bits are fractional, right? But this is all in my mind. This is not expressed in the code explicitly, right? I just have this, I know this because I multiplied it by that scalar. Okay? I think in the lab sheet I actually said to do 9 bits. So if you're doing 9 fractional bits, you would just say 512.0f. I can't remember which one. I use 8 bits or 9 bits fractional. Yes?
An idiotic question. Does it have to be multiplied by x, or can we just multiply it by, let's say, 10 to the power of something? Can we just multiply it? Let's say.
Sure. Oh yeah. If you can say pow f 2 comma 10 or 8 9. I don't know, whatever. 2. Yeah, you could do that. Sure. Yep. Yeah, that's fine.
Yeah, I've used it that way before. I've never done it with the hex before. I always use
No, that's not hex. That's decimal.
Yeah,
But
that's-
yeah.
I always use the power for it. So.
Yeah, that's no problem. Okay, so now when I do the transformation, I need to multiply the cosine value by like I, right? So I'm going to have like my loop 4i equals 0, 4j equals 0, and then inside that loop I'm going to say, I'm going to have like, I don't know, some transformed I. I'm going to say source I, s source underscore I, whatever you guys called it. Set that to be I times my cos value plus j times my sine value, or whatever I forget what the actual transformation is, but you guys get the idea, right? Something like this. You take I and multiply it by sine or cosine, and you add j times sine or cosine, whatever that transformation is to do the rotate. Okay? Now what's happening here is that, now you might say, wait a second, do I have to put I into fixed point format too? No, because I is a 32-bit number with 0 fractional bits. My cosine value is a 32-bit value with, in this case, 9 fractional bits. So if you remember your basic math, if I take a number with 0 fractional bits and I multiply it against a number with 9 fractional bits, then my product will also have 9 fractional bits. You guys with me? It's like, remember like in grade school, if you take like 2.5 and you multiply that by 2.5, right? You get a number with 2 digits, 2 fractional digits, right? Right? Because you have to add the number of fractional digits when you multiply 2 numbers and you put those in the product, right? The same thing applies here. Okay? Now, the other thing though is that when you add 2 fixed point numbers, you have to make sure that both numbers you're adding or subtracting have the same number of fractional bits, which is fine because we do, right? We've got that here. Because we'll have this sub-expression will have 9 fractional bits, and this sub-expression will have 9 fractional bits. So the sum, this value, will have 9 fractional bits. Okay? Now at some point, I'm going to have to extract the fractional bits, right? Because the interpolation requires you to extract. How do I extract the fractional bits? I can't use the same method you guys are using. Easy. You say source underscore I, and you use the AND symbol, the bitwise AND, and then you can use binary 1FF. 1FF is 9 1-bits. And so if I use a bit mask, this is a bit mask operation, if I AND the fixed point number with 9 1-bits in the least significant 9 bits, this will extract the fractional portion. Right? This will evaluate to the fractional bits. It's pretty cool, right? What if I want to say 1 minus the fractional bits because I'm doing the interpolation? Well, that's easy too, because a 1, in this format, a 1 would simply be 2 to the 9th power. It would be 512, right? So if I take 512, if I take 512 and subtract this fractional bits, that will give me the 1 minus the fractional part in 9-bit fixed point. Make sense? Now, if Charles were here, he'd say, that's an awful way to do it, because you just put a magic number in your code. What that means is a magic number means that if I want to change the number of fractional bits, I'm screwed, because I got to go through my code and find all these magic numbers and modify them. It would be better if I did it this way. Instead of having a hard-coded value, I can say 1 left shifted by 9, or better yet, replace that 9 with a constant that says f. And then at the top of my code, I can say pound define f to be 9. Also, I could use f over here too. So now my code has this parameter f that will allow me to adjust the decimal point wherever I want, and then I just have to recompile to change the fixed point bits. And I agree with them, but I'm not a very good programmer, so I tend to use the magic numbers. But it's better to do this. If you're a good programmer, you'll have your code parameterized, allowing you to make one change, and it'll have it percolate all the way through your code and be able to update the number of fractional bits. Not that you'll really need to, though, because 9 bits, 8 bits is fine for this assignment. But it's a good habit to get into as a programming practice. Any questions about that? Okay, so there's a couple details I'm leaving out here, but I'll come back to that in a minute. Okay, so Lab 3. So the purpose of Lab 3 is we want to do some analysis and some tweaking of the performance. So I gave you 2 tweaks right off the get-go that you can apply right away. Compile optimization, hardware floating point instructions. Do those right away. We want to add the performance counters, delete the interval timer. Also, make sure that, and I think you're fine, but make sure that in your NIOS processor, this is actually an out-of-date screenshot because they don't even have I don't know if they have the S anymore. They have different versions of the NIOS processor. Make sure yours is the F model. The F stands for fast. It's the largest, most powerful NIOS. Also, make sure that, I think this has been updated too. I'm sorry, I might have to go back and update this screenshot. I think this window has been updated in the new version, but make sure the hardware multiply is turned on. I'm pretty sure that these are on by default, so I wouldn't worry about those. But I'll have to go update that screenshot. Also, that needs to be updated. Sorry. Yeah, sorry. I'll have to update this screenshot. So just to give you an idea, this is what it looked like last year. There was an option here for floating point. You would add the floating point instructions in this screen. You don't do that anymore. You add them in the platform designer tool. You add them as a module, right? So forget that. I'll fix that. Okay, now the other thing about this is the floating point stuff, converting fixed point to floating point is a software strategy for improving performance. How do we do hardware improvements? How do we speed up the hardware? Well, we added the floating point stuff, but after we do fixed point, if we still need more speed, what do we do? Well, clock, that's an option. Another option is if we find that the number of cycles per instruction, now I don't know what you guys are going to get, by the way. Everyone's project seems to differ with this stuff, right? You guys are going to get different numbers. The number of cycles per instruction ought to be 1, ideally, right? It's a pipeline processor, it's RISC. There's no reason why we can't get 1 instruction per cycle most of the time, or it should be damn near. Or 1 cycle per instruction, instruction per cycle, should be 1 either way, right? If you get a cycle per instruction that's higher, and I suspect you will, we still don't know exactly what it is. Could be a variety of reasons for that, but usually the biggest reason for getting high CPIs is the cache misses. Because like I said, if you get a cache miss, there's no way for instructions that are behind the instruction that caused the cache miss to skip in line. There's no bypasses. There's no out of order. All the instructions in any embedded processor are executed in their program order. There's no way for them to be rearranged. On an Intel processor, it'll do that, but not on an embedded processor, because that's really one of the defining differences, by the way, between a desktop processor and an embedded processor. That's the biggest difference you'll find. Desktop and server processors use out of order dynamic instruction scheduling. Embedded processors don't. Anyway, so the point is that we make the cache bigger. If you make the cache bigger, you might be able to reduce the cache miss rate and thus reduce the average number of stalls experienced per instruction in your code. You guys with me? Now you might say, wait a second though, why are you assuming that it's the cache? I mean, it could be too many branch instructions, could be other reasons for stalls. Agreed, yes, I don't know. I don't know how much the cache size will impact your program. It might. I mean, think about it though, guys. You guys are doing the my image, your cat, the Gamecock image. My image is in memory, right? And you guys are accessing neighborhoods, right? When you do interpolation, you keep going to different pixels and looking at the neighbors, and the access pattern is all over the place, right? Because the interpolation code, you write the pixels in the frame buffer in order, right? Like when you guys write the output image, you do it in order. One pixel at a time, from left to right and from up to down, raster order. You do a raster scan. But that's the output. The input is kind of scrambled because for every output pixel, when you refer back to the input image, it can be anywhere. The image transformation function, the rotation transformation function, is determining the order in which you access the input pixels that are in memory. So you say, what's your point? My point is that you don't have very good locality necessarily. Your access locality is not very good with this application. So having a bigger cache might help. We want to examine that. So how do we do that? How do we check that? Easy. You go in the settings of the NIOS processor and you can tell it what cache size you want. So all you have to do to change your cache size is make one setting change and rebuild your hardware. You guys with me? It's pretty neat, right? You can't do that with a hardcore processor. You can't go and buy a processor from Intel and say, oh, I want a bigger cache. No, throw it away, buy a new one. But with an FPGA softcore processor, you have that ability. So, okay, so let's finally get to the brass tacks here. What do we need exactly for Lab 3? Well, as you might imagine, we want to we're building off your old lab. You need to have Lab 2. Yes. Yes. Yeah, I think this one should be pretty quick because you're not writing any new code, actually. All you're doing is, well, you're making a small tweak. Well, you are adding the fixed point code, but you're tweaking your old code. You're not writing any whole cloth code. So you go back to your old program. Obviously, you have to have Lab 2 working. If you don't, then you're gonna have to finish that first. And this is the part of the class where it's easy to start to fall behind if you're not caught up. This is also why we cap the late penalties. But go back to your old code, make the tweaks, measure instructions per pixel and cycles per pixel using the methods I described today, and then change your code to fixed point and do the same thing again. And then repeat that process again for having a 4 kilobyte cache, which is the default, which is what you've got now most likely, data cache. Remember, there's an instruction cache and a data cache, and a 16 kilobyte data cache, right? So now we've got a matrix, a 2 by 2. You can think of this like a table where you've got CPI, and you can have cycles per instruction, fixed, float, 4K, 16K. Sorry, 16 kilobytes. All right? And then you'll have CPI, 4 CPIs, right, for those 4 combinations. And then we also want to know CPI, and we want to know, well, what else we want? CPI, calculate speed up. All right, yeah, and the speed up of so obviously we expect, maybe it won't happen this way, but we expect fixed to be faster than float. So we should be able to get a speed up here and a speed up here. Right? So, you know, speed up, speed up, speed up, speed up. Right? And then we just want you to put those in a report. So, and you know, the report, we don't give any specific guidelines how to make the report, but just, I mean, basically just make a table and a couple paragraphs explanation. It just doesn't have to be more than a page or 2. Some people go crazy and they'll turn in like a 15-page report. We don't expect anything too elaborate, but it should be something we could read and be able to quickly see what your conclusion is. Conclusion being, what's the best way to get performance out of this thing? Cash or fixed point, right?
You have to.
And you could go both.
pursue both avenues? Or
Yeah, you can go both too. So you'll have a speed up, like for each cache size, you can go speed up from float to fixed. And then for fixed and float, you'll have speed ups relative to the,
So do you have to pursue both avenues, or could you just work on one?
no, you have to do both.
Okay.
Yeah, because we don't know which one's going to work. Yeah, so you can have a speed up here at the end of each row and at the end of each column, right? And then you could put one here that's for everything. So we're hoping to figure out, you know, what's the best strategy here. Yes?
Are we going to be like registering music or turning in something? We're not going to be demoing anything? Layout.
We need you to submit
Okay.
and submit your report and your code. I don't believe we're going to do demos for this one. Not much to demo. Obviously, you're going to have to demo it to yourself, so you have to ensure that it's working. And hopefully, you're going to be really impressed by how much faster your code is when you do this. Like, because right now you're seeing it paint real slow. What we're hoping that'll happen is you'll do this stuff and you'll see it just, it should be screaming fast, hopefully, after this. Hopefully. Or maybe none of this will do any good. I don't know. In the past, to be honest, usually some groups will have better results than other groups. It depends on your code and it depends on how much effort. We're going to be grading this mostly on your report, make sure you've done all the experiments and you've got all the data in there. And obviously we're looking for the numbers to be reasonable and make sense. If your code is 10 times slower when you increase the cache, obviously we know something's horribly wrong, right? Because there's no way that having a bigger cache will be, you know, significantly slower. It should be faster. But in the worst case scenario, it won't make much of a difference, right? And then, of course, we can go in your code and check and make sure you did that stuff, okay? I'm sorry?
We're not showing anything.
No. Just submission, and the report will be part of the submission.